Hello, everyone. We should be now live. Thank you very much. It's a very pleasure. So my name is Giacomo Beccari. On behalf of the ESO for Science and the Director of Science for Science, I'm very happy to welcome you to the first event of the ESO Hypatia Colloquium. So I would like to start by basically mentioning, so yes, just was checking that everything's fine, yes. So it was just to mention that, so just to give you a brief description, so we decided to start this series in last winter, and in November we released the call for applications. We received more than 300 abstracts from young astronomers. So basically the restriction was less than 3 years from the PhD at the time of the application, of course. We are really, so of course it was a very competitive selection process, and we would like to first congratulate with the 42 speakers that we will host during this series of talks. But we would like to, personally, I would like to encourage, to congratulate to everyone who applied. We really, the committee was really impressed by the great excellence and diversity of science topic and all the research that is clearly done these days in our community by the young astronomers. We are really happy to see this, to watch this. You are basically the engine of the present and future of the astronomical research. So please don't feel discouraged. Please keep doing what you do. Be enthusiastic about science and about astronomy, about research, and we are there to support you and to help with this and other ways, basically. So don't feel discouraged, but feel very proud, because this is really, it was really a pleasure to see this happening. Some technical info related to the talk of today and to the talk in general. As you might have seen, you can basically you can join the series either by registering, and so by registering, basically there is a form on our Hypatia pages, and there you can basically then you register this way. You will be sent a link to which you can directly enter with us in this virtual colloquia, and they are in our virtual room, basically. Or you can also watch the talk on YouTube, because we are streaming live on YouTube. In this case, so in both cases, you can, of course, so each event foresees 2 talks of 20 minutes plus 10 minutes of questions, so it's a 30-minute slot for each candidate. You can make questions, so the registered attendee can make questions from inside basically the meeting using the raise hand feature that is available. Otherwise, people on YouTube, they can make a question using the chat, or they can use also a form that is available on our pages. They can be filled with a question and sent, and we are monitoring email. So we are receiving these live, so we can answer. We can basically then redirect the questions to the speakers. So talking about speakers, I think this is all for the technicalities. We can then, the speaker of today, here I have a slide. We have Virginia Cuciti and Boy Lankhaar. These are the title of the talk that I show you here. But now I think I would like to, and it will be sharing, will be myself today, and I have a co-chair with me, which is Aishwarya Gindar, which is a student, and is a student from, which is an expert in galaxy formation and evolution and AGN, and she will be helping me in chairing, and she will be basically chairing the second event, the second seminar. So now I can stop sharing so that everyone can come online. Yes, you should be there. So how are you? Hi Aish, hi Virginia, hi Boy, how are you? All fine? Very good. So very happy, we are very happy to have you here. As I said, so I think I said everything I wanted to say regarding the seminar. So now we start with Virginia. Virginia got the PhD in 2018 in astrophysics at the University of Bologna. And then currently she got an Alexander von Humboldt Fellow at the observatory in Hamburg, where she is currently doing her research. And she will be presenting Clash of Giants, radio emission from merging galaxy clusters. Virginia, yes? You cannot talk? I cannot talk. You cannot, okay, sorry. Probably there is, sorry, technicalities. Give me just 1 second. Yes, I see. Sorry, probably. Try now. Yeah.
Okay, it worked.
Yes.
I did not have the permission to unmute myself.
I had the power. sorry, very good. Excellent.
Okay,
excellent.
I'm gonna share my screen.
You know, this is me. Whatever I try to do, I mean, I always make mistakes. There is no thing, I mean, it can prevent this. I'm so sorry about that. But this is, you know, this is me.
Don't worry, no more.
So we are happy to have you here. And as I said, you have in total 30 minutes. Today we have I took a bit of time at the beginning, sorry, just to introduce the event, but now you have 30 minutes, so you can start. And then we will do the question session after. Thank you very much.
Thank you. So first of all, let me thank the organizers, not only for giving me the opportunity to give this talk, but in general for organizing this series of events, especially in this period where it's particularly difficult for us to show to the community our work. So today I will talk about the radio emission that we see in the radio band, of course, when galaxy clusters crash against each other. I prepared this talk thinking about a broad and diverse audience. So for an expert view, it might seem a bit oversimplified, but I hope that in this way it will be enjoyable also for people that are not experts in the field. So this is the outline of the talk. I will start with a very general introduction on galaxy clusters and on the radio diffuse sources that we see in galaxy clusters. Then I will focus on one particular type of radio source that is called radio halos. I will give a theoretical and an observational overview on halos, and I will also try to highlight the main open questions that we still have in this field. And in the last part of the talk, I will tell you what are the plans to try to address these open questions. So let's start with galaxy clusters. This is a frame from the Millennium simulation where we see the large-scale distribution of the dark our universe. The dark matter forms these filaments in the cosmic web and these knots. The knots are the place where galaxy clusters form. Galaxy clusters have typical masses of 10 to the 14, 15 solar masses, and they are made of thousands of galaxies. So if we observe a galaxy cluster in the optical, this is what we may see. However, these galaxies only account for a few % of the total mass of the cluster, because the vast majority of the mass is actually in the dark matter. The dark matter can also be studied with optical observations, but this time focusing on the effect that the cluster has on distant galaxies, so on the weak lensing effect. So this is the weak lensing map of the same galaxy clusters, which tells us basically the distribution of the dark matter. Another key ingredient of galaxy clusters is the so-called intercluster medium. It accounts for 15–20% of the total mass of the cluster, and it's a very hot and rarefied plasma that permeates the space between the galaxies. This plasma emits via thermal Bremsstrahlung in the X-rays. So if we observe again the same galaxy clusters in the X-rays, we basically see the distribution of the intracluster medium. But what if we observe this cluster in the radio band? The picture is quite different. These structures that we see here are tracing cosmic ray electrons and magnetic fields and are producing synchrotron radiation. This is the general picture of this particular cluster, which is called toothbrush galaxy cluster, where when we put together all the information coming from different wavelengths. But let's focus on the radio wavelength and let's give a name to these structures that we see. So this one at the periphery of the cluster, this elongated structure here, it's called radio relic. Actually, radio relic is a bit of an old name. Today we tend to call them cluster radio shock. And the one here at the center, more diffuse and faint, is called radio halo. Now let's go a bit more into the details of these radio sources. First of all, they are not only found in that particular cluster, but there are many clusters showing radio halos and radio relics. Both radio halos and relics are on the scale of the megaparsec. Radio halos are found at the center of clusters, and their morphology roughly follows the X-ray morphology of the ICM. Radio relics instead are found at the periphery of clusters, and they have these elongated or arc-like shapes. Let's see how these radio sources form. We believe that their formation is tightly connected to the formation of the galaxy cluster itself. So in the hierarchical view of structure formation, galaxy clusters form via the merger of smaller substructures. So here, let's imagine we have two galaxy clusters, they collide, they merge into a larger galaxy cluster, and merging events can release energies up to 10 to the 63 ergs in a time scale of about 1 gigayear. Part of this huge amount of energy goes into shock waves and turbulence that develop in the intercluster medium. This is a video of a simulation of two merging clusters. The green is basically the intracluster medium. So here we see that when two galaxy clusters merge, these shock waves are produced in the center of the cluster, and then they travel towards the outskirts, while turbulence is produced here in the center. Both shock waves and turbulence can accelerate electrons in the ICM, and then these electrons move through the cluster magnetic field and produce synchrotron radiation that we observe in the radio band. This is an actual observation of a cluster. The green is the X-ray emission and the color is the radio. So this source here is a radio relic tracing the particles that have been accelerated at a shock front similar to the one that we see here in this simulation. But now let me focus on radio halos because those are the focus of my research. So from a theoretical point of view, we believe that radio halos form when turbulence is injected in the intracluster medium during a merger event. This turbulence accelerates electron via mechanism of Fermi-2 acceleration. The efficiency of the turbulent acceleration depends on the amount of energy that you have available from the merger, which in turn depend on the mass of the clusters and on the type of merger. So more major mergers are more energetic than minor mergers. This plot here shows some possible radio spectra that radio halos can have in this theoretical background. The spectrum is basically the radio power versus the frequency. And when I say spectra, I will say spectral index several times. I mean the steepness, the slope of the spectral energy distribution in the radio. So the idea of the model, very simple, is that massive clusters that undergo energetic merger event typically have spectral index of about 1.2, 1.3, like this one here on the right. I'm calling here those radio halos classical radio halo spectra simply because they were the first to be discovered, and the reason is because they emit energy up to gigahertz frequency, which is the classical radio frequency that we use to observe. However, the main prediction is that all the less energetic events, the less massive clusters, should form radio halos with very steep spectra that we call ultra-steep spectrum radio halos. Those are only visible at low frequency. We have actually observed some of them, but the idea is that since less energetic events are more common in the universe, once you are able to observe systematically at low frequency, you should see a large population of ultra-steep spectrum halos coming up. The problem here is that observing at low frequency is much more challenging than observing at high frequencies. In this theoretical background, now we can derive some basic expectations on the statistical properties of radio halos. The first one, which might be a bit obvious at this point, is that radio halos should be found in merging clusters, because the merger is the event that injects turbulence in the ICM. The second one is that since the mass that gives you the amount of energy for particle acceleration, the radio power should correlate with the mass. The other ingredient is the merging event, so the radio power should somehow also be connected with the merger state of the cluster. Another expectation is that the fraction of radio halos should increase with the mass. This is a theoretical plot where we have the probability of forming radio halos as a function of the mass. And you can see that this probability in general increases. And also, and this is the last expectation, the fraction of clusters with radio halos is expected to increase towards the low frequencies. And this is because at low frequency you expect to see the population of ultra steep spectrum radio halos that you can only observe at those frequencies. Now let's keep in mind this expectation. Let's copy them in the next slides while I will review the observed statistical properties of radio halos. Now, the study of the statistical properties of radio halos has been going on for the past 20 years or so. So some of the results I'm going to show now have been known for a while, but the plots, the things that I will discuss are all recently been derived with the largest sample of galaxy clusters with observations at frequency larger than 600 megahertz. And let's see which one of these expectations we did actually check. Let's start with the radio halos are emerging galaxy clusters. So this is what we call a morphological diagram. Both the concentration and the centroid shift parameters are parameters derived from the X-ray observations, and they give us information about the dynamical state of clusters. The only important thing here to keep in mind is that here we see relaxed clusters, and here we have the merging clusters. In this plot, I colored radio halos in red and non-radio halo clusters in black. So what we learn from this plot is that more than the 90% of radio halos are found in merging clusters. So we can check the first expectation of the model. Let's focus on the radio power mass diagram. There is actually correlation between the radio power of radio halos and the mass cluster. So more powerful radio halos are found in more massive clusters. Clusters without radio halos are here, I use them as upper limits, and they lie well below this correlation. So we can also check the second expectation. Now let's focus a bit on this diagram. Here we have to think that the radio halo is a transitory phenomenon during the lifetime of a galaxy cluster. So for example, we can think about the cluster that is relaxed, is somewhere below here, we don't know exactly where. And then at some point it undergoes a merger event. So it goes up, it moves up in this plot, up to the correlation, where it appears as a merging cluster with radio halo. Then it relaxes, the radio halo fades away, and it goes back to the region farther below with respect to the correlation. If this picture is correct, what we expect is, one, that the scatter of the correlation should be quite large, and this is actually what we observe. And the second thing is that the scatter of the correlation should be connected with the merger state of the clusters. Let's see if we actually see that. In this plot, we have on the y-axis the distance, the vertical distance from the correlation. And on the x-axis, we put basically a slice, a diagonal slice of this plot here. So here we have clusters that are more relaxed on the left, and then they become increasingly disturbed going to the right. What we learn from this plot is that the galaxy clusters that are scattered up with respect to the correlation, so these ones here, these radio halos here, are all found in the most disturbed systems. On the contrary, the radio halos that are below the correlation are those found in the least disturbed systems. So we can say that yes, also the radio power of radio halos is associated with the merging state of clusters. What about the fraction of clusters with radio halos? This is a plot similar to the one I showed at the beginning. It shows the expected fraction of radio halos as a function of mass with observation at 600 megahertz, because those were the observations that we had in this work. What do we observe? So we observe a fraction of clusters with radio halos in high mass cluster of about 75%, while the fraction of radio halos is about 35% in low mass clusters. So we do see that the fraction of clusters with radio halo increases with mass. And actually the fractions that we see are quite in good agreement with expectation of the model. What about the low frequency? The blue line here is the expected fraction of radio halos as a function of mass with observation at 140 megahertz. So as I said, the fraction is expected to increase, but in particular, it is expected to increase a lot in the low mass regime, because here is where we expect to find the population of ultra steep spectrum radio halos associated with less energetic events. This one is still a question mark. And this brings me to the main open questions that we have in this field. So do we actually observe the expected population of ultra steep spectrum radio halos at low frequency? The second question is related to the fact that the majority of the work so far is limited to high mass clusters. So mass is larger than 5-6 times 10 to the 14 solar masses. But we don't know what happens in low mass clusters. Does the fraction of radio halo drop further? Does the correlation still hold in this mass regime? The other question that we still have regards high redshift clusters. Here I didn't have time to go into the details of high redshift clusters, but the idea of the model is that at high redshift, we should see a decreasing fraction of radio halos, and these radio halos have steep spectra, mainly because the inverse Compton losses are more dominant at high redshift. Why don't we have already the answers to these questions? Because they all need low frequency sensitive observation to be addressed. So now, in the last part of the talk, I will tell you what we plan to try to address these questions. We plan to use the low frequency array, or LOFAR, which is a radio interferometer in Europe. The core is in the Netherlands, but then all the stations are spread all around Europe. LOFAR has two types of antennas: the LOFAR high band antennas operating between 120 and 240 megahertz, and the low band antennas operating between 10 and 90 megahertz. But why is LOFAR so powerful in the study of galaxy clusters? There are two main reasons. The first one I kind of already mentioned, and it's the low observational frequency, which makes us sensitive to the steep spectrum sources, such as radio halos, for example. And the second one is the combination of the sensitivity to the large-scale emission and resolution that we have with LOFAR. The sensitivity to large-scale emission is given by the dense core of LOFAR, and it's the one that gives us the possibility to actually image such huge sources in the sky, such as the radio halo in the Coma cluster, for example. The resolution instead is given by the long baselines of LOFAR, and it's the one that enables us to disentangle the contribution of the discrete sources embedded in the diffuse emission. Now, this is a series of images that I choose. Of course, it's not exhaustive at all. These are all LOFAR images, and they're not only pretty pictures, because actually some of them really show some new type of source or some new type of mechanism that we discovered with LOFAR in galaxy class. For example, if we focus on these two images here, we have two systems in a pre-merger state. So this is the one galaxy cluster, this is another, and here we have a similar situation. They both have a radio halo at the center, but Lankhaar for the first time discovered diffuse emission also in between the pre-merging clusters. Or this one, for example, this part of this tail here is called gently re-energized tail, because here we discovered a completely new mechanism of acceleration taking place in the intracluster medium. Now, unfortunately, I don't have time to go through all these results, although I would like to. But in the last part of the talk, I would like to go back to the statistical work that we are doing with Lankhaar and in the galaxy clusters field. So we recently selected more than 300 clusters from the Planck catalog. All of them have Lankhaar HBA observations, so 140 megas from the data release 2 of the Lankhaar 2 survey. The plan that we have is to divide this huge sample into statistically meaningful subsamples. And for example, we can imagine a relatively low redshift high mass sample where we can study the occurrence of radio halos as a function of mass and dynamics, similarly to what I have shown before, but this time at low frequency. We can do the correlation at low frequency and also extending to the low mass clusters. And for the first time, we will be able to do statistical spectral studies, because for the majority of these clusters, we already have observation at higher and or lower frequencies. We will also perform the first statistical studies in very low mass clusters and also at high redshift. For the high redshift part, actually, we already have some nice results, and I encourage you to have a look at this paper from Gabriella Di Gennaro. Now, these are my conclusions. Radio observations of samples of few tens of clusters at frequency of about gigahertz have revealed that radio halos are found in merging galaxy clusters. The radio power of radio halos correlates with the mass of the host clusters. Also, the scatter of the correlation is connected with the merger state of the host cluster, and the fraction of radio halos increases with the mass of the cluster. All these findings seem to be in very good agreement with the expectations of turbulent acceleration models. However, there are some open questions that need low frequency observations to be addressed. And what we're doing now is to analyze the largest sample of clusters with Lankhaar HBA observations. And I will thank you.
Very good. Thank you very much, Virginia. Thank you for very perfect on time. So, so I see clapping people, clapping to you. So as you know, there is a delay of 30 seconds between basically what we do here inside the chat, beside the Zoom and YouTube. But in the meantime, I would like to ask if there are questions now from the people in the participants in Zoom. If someone wants to make a question to Virginia. I see one hand raised. Let me see. Should go. Yes. Please, can you turn on your microphone, Ilsang? And you can make a question. Hi.
Do you hear me?
Yes, perfectly.
Yeah.
Thank you. Thanks for the very nice talk.
Thank you.
My question, basically is, can you use your observational studies of these radio halo properties to give a sort of constraint the mass ratio of the two, the progenitor clusters? So will that observational properties be depending on the ratio of the masses of the progenitor clusters?
So yeah, it does depend on the ratio, because as I said, major mergers behave differently with respect to minor mergers, for example. The problem is that it's not, the link is not so straightforward, because that it's not the only player that we have. So we have no formula that tells us what was the progenitor mass given a radio power, for example. Because there is also, like, as I said, also the time of the time scale of the merger and the moment where we observe the radio halo, that makes a lot of difference. So if we observe it at the beginning or during the peak of the radio halo emission or at the end, even if the progenitor were the same, we would see a different radio power. But the two things, of course, are somehow related. The problem is that there is no direct connection or easy connection.
Thank you.
You're welcome.
Great. So we have a second question from Emanuela. I think I saw Emanuela Pompei.
Yeah, sorry, it was partially related with the previous question, but I'm also curious about the scatter of the correlation, because you saw this in the plot, you show a parabola, but I'm curious how much this correlation is not degenerate. I mean, can the scatter be just due to the error measurements or misidentification of the clusters?
Yeah, sure. Yeah, the fact that the scatter is connected to the merger state is something that we kind of expected, and we were happy to be able to see it for the first time. But of course, that's not at all the only player there. So I don't know why this stopped. Okay, so yeah, of course, the scatter is a combination thing. Of course, there is a scatter intrinsic to the correlation. There will be for sure some scatter given by the errors. Some of it, as we see here in this plot, is also connected to the merger state.
Thanks.
Great. Thank you very much. So is other question from Virginia from the chat? Or from YouTube exploded with thank you, just to tell you, Virginia, there was and great talk. So there was just to let you know. So because otherwise I don't see your eyes then. Maybe I can. So Virginia, and I apologize immediately with because this is not my field of absolutely, and so I apologize with you and everyone else because it might be. So, but I wanted to ask in particular for this plot that you see here on the right hand side, the increasing distribution. I think this is the same as it was in slide 9. I think it was bigger, right?
Yeah.
I wanted to ask you because I really don't know. So this is. The fact that this plot shows a dynamical state of the galaxies, right, or the clusters.
See, yeah, this is the dynamical state of.
But what I wanted to ask you is this purely. So this correlation is purely empirical. So you have an empirical method to assess that. So how do you know that this is? You see, to infer the dynamical state from this. So do you see?
No, the dynamical state is inferred from the value of these parameters. As I said, unfortunately, I didn't have time to explain these parameters, but just to give you very, very simple. So the concentration parameter, basically, as I said, they are derived from X-ray observations. So the concentration parameter tells you how much the X-ray surface brightness is concentrated in the center. Okay. So very briefly, the cool core cluster, if you know what I mean, so that the most relaxed clusters have high concentration parameters because they are very peaked at the center.
Okay.
So here are the cool core cluster, and here, when you go down, they are more and more disturbed. The centroid shift instead gives you an idea of how much the centroid and the peak of the X-ray emission are far apart. So if they are a lot far apart, it means that the surface brightness is all messy and disturbed. If they are one on top of the other, again, it means that the surface brightness is very peaked. So the centroid shift, like here on the right, you have the most disturbed, and on the left, you have the less disturbed. So the correlation, the trend is empirical, yes, but the reason why we say here we have merging clusters and here we have relaxed clusters is because of the values of these parameters.
Okay, I see. Thank you, very fascinating. Thank you very much.
Thank you.
Thank you. So is there
Stop
no more questions? I don't see. Still, we are basically next to the end. And so, okay, so I will thank Virginia. Thank you very much.
Thank you very much again.
But stay online, please. Don't
Yeah, I will, of course.
if you can. Okay, if you can. But it was really a pleasure, and congratulations for being the first opening the new series.
Yeah, it was a great pleasure
Exactly.
to open this series of talk.
Great. So now I will leave the floor to Aish, who she will chair the session. I will be helping in the background, and Boy will be the next speaker. Please, Aish.
Thank you, Giacomo. Thank you, Virginia, for the very nice talk. And hello to everyone who has tuned in for the session today. Next, I would like to invite Boy Lankhaar, who is a PhD student at the Chalmers Institute of Technology, Chalmers University of Technology, sorry. And he would be talking about studying these cosmic magnetic fields and tracing them using molecules. So over to you, Boy.
Yes, thank you, and thanks very much to the organizers here to give me this opportunity to present to you all of this work. So I'm going to be talking about tracing cosmic magnetic fields using molecules, and this is based on my PhD thesis. I actually sent my PhD thesis yesterday to the printers, so it's now in print, and I will be defending it at the end of this month. I did all of this work together with these people. And yeah, so we're going to be talking about tracing cosmic magnetic fields using molecules. And I'm sure that a lot of you are going to be familiar with tracing magnetic fields using dust polarization. So I'll be first introducing a little bit dust polarization, and then I'm going to try to convince you that magnetic field tracing using molecules actually provides for a more robust method to detect magnetic fields. This comes at a price because it's a little bit harder observationally, but it's an opportunity nonetheless. I'll be focusing as an application mostly on protoplanetary disks, but I'll be sure also to include some examples of other astrophysical sources. So these are 3 maps of dust observations spanning 6 orders of magnitude in scale. So on the left-hand side, we have the Whirlpool galaxy. These are actually Hubble images overlaid with dust polarization images. Then we have the Taurus molecular cloud here in the middle of these are Planck observations, and then we have the star-forming region NGC 133 IRAS-4A. And I think what is done most beautifully in the image of the Taurus molecular cloud is that there is a sense of direction which is drawn in this image. It's almost as if Van Gogh has drawn up this image. And the sense of direction is supposed to represent a certain preferred direction in the radiation that is emitted from these regions. The preferred direction is called then the polarization. But why is there this polarization in the dust emission? So this is a cartoon I swiped from a presentation from B.G. Anderson, which shows you 2 extremes of the rotation of these dust particles that are embedded in the astrophysical objects. On the left-hand side, we have the extreme of chaotic rotation. So the rotation vectors, they're all misaligned. They're all pointing at a different direction. The rotation is with respect to a random principal axis. And when this is the case, the radiation coming from these particles will have no preferred direction, or in other words, it will not be polarized. This can be contrasted to the other extreme, where all of the rotation vectors of the dust particles are lined up. The rotation is then with respect to some shared fixed principal axis. This will then lead to the fact that radiation will have a preferred direction or will be polarized. Now, and in the case for most dust particles in astrophysical region, there is one dominant alignment mechanism that is in play, and this is the radiative torque alignment mechanism. you have an anisotropic radiation field spinning up the dust grains, which then subsequently relax to orient themselves perpendicular to the magnetic field direction. So the polarization will then be oriented with respect to the polarization, to the magnetic field direction. So the maps that I just showed you are actually maps of the magnetic field through these dust polarization observations. And the magnetic field in the Whirlpool galaxy, for instance, is oriented quite neatly, at least in the inner parts, to the spiral arms. And in the Taurus molecular cloud, you also have a magnetic field, which has its direction sustained over quite large spaces. And this fact can actually be squared quite neatly with magnetic field strength observations using, for instance, Zeeman observations, which show that the magnetic field strengths lead to energies, magnetic energies, which are comparable to the turbulent energy present in molecular clouds, and often way higher than thermal energies and comparable to the gravitation. So really the magnetic field is a force to be reckoned with. It really is a part of the dynamics of these astrophysical regions, which has to be incorporated. But if we now go on to protoplanetary disks, we go even one more order of magnitude in scale lower to ALMA observations of the HL Tau protoplanetary disk. And these are observations of the dust polarization. These come from Stevens et al. And Kataoka from 2017. And if we now look at the polarization morphology of at these different wavelengths, then we can see that there's a different polarization morphology for each image. And you would not expect this if all of the particles would be aligned to the magnetic field. And indeed, it is actually not the case that in protoplanetary disks, dust particles align themselves with the magnetic field. It are other alignment mechanisms that are in play. For instance, for the 3.1 millimeter observations, the particles will align themselves to the radiation anisotropy, and for the shorter wavelengths, it will be self-scattering that dominates the polarization signals. So these observations are extremely interesting because they'll teach you about the size distribution or the dust properties in these protoplanetary disks, but what they won't teach you is something about the magnetic field. And it's not like the magnetic field in protoplanetary disks isn't there. And I think this is most beautifully illustrated, or most beautifully illustrated for the disk TW Hydro, where we know from stellar surface magnetic field observations using Zeeman observations that the magnetic field there is about 3 kilogauss. This magnetic field has to be advected from cloud magnetic fields through the disk. So the magnetic field has to increase its strength towards the stellar surface. And this leads you to conclude that the magnetic field there is actually should actually be quite strong, so much so as to influence properties like the accretion, the turbulence, even planet formation in these protoplanetary disks. But to exactly quantify what the effects will be, you will need both observations of the magnetic field strength and morphology. And we're going to try to do this with molecular line polarization. Molecular line polarization happens through an effect called the Goldreich-Gilafis effect. And I will try to convince you that the polarization due to the Goldreich-Gilafis effect will be more robustly tracing the magnetic field direction. So the Goldreich-Gilafis effect describes the alignment of molecules, and the alignment mechanisms are actually quite the same as those for dust, for the dust via the radiative torque alignment mechanisms. And there's really 2 processes that we should include, or that we should think about when we think about the alignment properties of molecules in astrophysical regions. First of all, we have collisions. And if you think about collisions, a collision between two molecules. It can come from any angle. It can come from anywhere. So it's really isotropic. So if collisions are dominant in the molecular excitation, then the rotation vectors of all of these molecules, they will be randomly oriented, and it will not give rise to any polarization in the emission. However, if we have radiative excitation, there is some potential for the lines to get polarized. If you imagine a source of light coming from one direction and a bunch of molecules as lit up from this source of light, then the molecules that interact with the radiation field will orient themselves along the radiation field, just like a flag would in the wind. And then you would get these aligned rotation vectors, and it will then give rise to polarization in the emission. Now, we've recently built a code. It's called Portal. It stands for Polarized Radiative Transfer Adapted to Lines. You can read about it in this paper or get it from this GitHub. And in Portal, we comprehensively model also the alignment of both collisions and radiative excitation events. And you can imagine that to estimate the subsequent alignment of the molecules, you really have to know the radiation anisotropy. What Portal does is for any astrophysical region, it maps out at any point in this astrophysical region the radiation anisotropy and computes then at any point in the simulation how the molecules will align themselves to the magnetic field. Then afterwards you have a ray tracing, and it will give you a polarized image dependent on some magnetic field. But I keep saying that line polarization traces the magnetic field very robustly. I will now try to explain why this is. So suppose we have a bunch of aligned molecules. There's an anisotropic radiation source aligning all of these molecules. Then the significant interaction processes that happen there have all a certain rate. So for a molecule such as CO at these densities, the rate of radiative events that then lead to the alignment of the molecules happens about 1 time every 10 million seconds, and the same goes for collisional events. However, for molecules, the magnetic precession rate, the rate at which these molecules precess around the magnetic axis, is once every second. So after each radiative or collisional event, the molecule has ample time to reorient itself to the magnetic field. And this is so for almost any molecule in any astrophysical region. Since all of these molecules align themselves then back to the magnetic field, the polarization from these species will always be polarized with respect to the magnetic field. Now, there's one caveat to this, and that is that unfortunately, the alignment can be either parallel or perpendicular to the magnetic field direction. You really need to model the radiation anisotropy with a code such as Portal to know which of the two it is. So as to interpret the polarization signal from these molecules properly. So now I've gone on about the theory of line polarization. Let me show you some simulations that we did using a Portal. So these are simulations of a protoplanetary disk. It is TW Hydra at this distance, and these are simulations of HCN and CO in the TW Hydra disk. Why HCN and CO? CO is of course the most abundant molecule. However, its dipole moment is quite low, and since it's the radiative excitations that give rise to polarization, it's not actually a very good candidate for polarization observations. So as a molecule with a very large dipole moment, we have HCN, which has way stronger radiative interaction, so way stronger potential to get polarized. So this image shows you on the y-axis the polarized intensity predicted with Portal, and on the x-axis there's the offset from the center. And I've azimuthally averaged this because TW Hydra is almost a face-on disk, so then this can be done. And as you can see from these simulations, really the HCN is expected to be polarized significantly in the inner regions of the protoplanetary disk, and in these regions would hold information on the magnetic field structure of the disk. CO, on the other hand, is polarized a bit farther out, but the polarized intensity is really too low to be seen with ALMA without a very long integration times. And I think this is also what we have seen in observations that have been done so far. So 3D polarized radiative transfer modeling from Portal predicts that these molecular line polarization observations are really feasible, but require a molecule with a high dipole moment. Now, where else could you find line polarization observations? I particularly like AGP circumstellar envelopes from Maser magnetic field strength observations. We have learned that the magnetic fields of these regions are actually quite high, and it could be that the magnetic field is shaping the outflow of the AGP circumstellar envelopes, which might be a factor in explaining the very elaborate morphologies from planetary nebulae. So these are CO observations, and you can see that the line polarization is quite high here, and these observations are being interpreted now using Portal. So another one, another example, which I think is quite exotic, at least for my general interest, is the AGN. You have these embedded AGNs with very large column densities. They're called COMS, compact obscured nuclei, ARP220 and NGC4418. The nuclei are two examples of these structures, and they show towards their center very strong emission in the vibrationally excited HCN transitions. And this is because of the dust close to the center is heated up to hundreds of Kelvin, and so much so as to excite the HCN to its vibrational excited bending mode. Now, the nature of these emission from the vibrationally excited HCN makes it so that the polarization fractions are actually quite high for these species. We predict that they can be polarized up to 15% towards the center of these COM structures. And this is indeed very interesting because it is from these regions that there is also an outflow being launched. Other applications could be in molecular clouds, for instance, through characterizing the MHD turbulence and adding to the many methods that already exist to characterize MHD turbulence. So now I'd like to move back to protoplanetary disks. These are Zeeman observations. These are Zeeman observations of TW Hydra. TW Hydra is a face-on disk, and if you have Zeeman observations, you're sensitive to the line of sight component of the magnetic field. So you're really sensitive in TW Hydra to the vertical component of the magnetic field in this protoplanetary disk, which is very important for the accretion processes going on there. These are ALMA band 6 CN observations. You can see them here, but really the Zeeman splitting was too weak to be detectable in this source. It comes from the inner part, and this is CN observations of the inner part of the protoplanetary disk. And you would expect in the Stokes V spectrum a really nice S-shaped profile, which we really didn't see, but it does place very stringent constraints on the magnetic field strength of the source. this source, and also places a constraint on the toroidal magnetic field because of its very low inclination. I also like to tell you about molecular ion polarization, which I think could be a nice opportunity to detect the process of ambipolar diffusion. Ambipolar diffusion is a common non-ideal MHD effect. It's very important to magnetic field transport, but it's notoriously difficult to detect, and it's particularly important in star formation, for instance. Now, and we base this effect on old molecular beam experiments that experimental molecular physicists did in the 70s. And in these molecular beam experiments, they have a certain molecular gas, which they expand together with the carrier gas. And what they found was that the carrier gas and the molecular gas of interest, they had a little velocity slip. So the collisions between these two phases had a preferred orientation. And what they then saw was polarization coming from these molecular beams. And a similar effect happens in ambipolar diffusion, where you have a charged medium and a neutral medium that have a velocity drift between each other. So if you would have molecular ions as part of the charged medium and neutral medium represented by H2, then the collisions between these two molecules would have a preferred direction. Oriented collisions means a net alignment in the molecular ions. And thus also would lead to polarization in the emission. And we presented this hypothesis in this letter. The black line here is of interest, and for very strong drift velocities, we expect very high polarization fractions, up to 1% if the drift velocity is about 10% of the thermal velocity. The polarization then indicates the magnetic field direction, but it also would be a direct indication for the process of ambipolar diffusion. Now, finally, I'd like to talk a little bit about masers, about methanol masers in specific masers. They're excited at very specific regions in the universe, and methanol masers, specifically the 6.7 gigahertz masers, are exclusively excited around high mass star forming regions at very specific regions at some hundreds of 500 to 1,000 AU from the central protostar in the accretion disk. And recently, we've been measuring the polarization of these masers, and they show that the linear polarization is consistent with dust polarization observations. So this really traces the magnetic field direction. And we've last 2 years ago, we've presented this code CHAMP that can characterize the linear polarization of these masers. Methanol masers are also particularly suited to circular polarization measurements. Their emission is extremely strong, very narrow, which makes them very suitable for Zeeman observations. And these have now been made possible by the new G factors that we calculated for methanol that make the proper interpretation of these methanol maser circular polarization signals possible. This led to a reinterpretation of old results, and it seems to be showing that methanol masers that really trace a region where the magnetic field is dominant in is dynamically important, and this is very close to the protostars. So let me conclude. I've told you about molecular line polarization, and what I hope you take away is that it very robustly traces the magnetic field direction. I've showed some portal simulations of protoplanetary disks, and they seem to, and they show that that these molecular line polarization are really observations are really feasible. It can also be done in other astrophysical regions, AGB stars, cons, for instance, but also outflows, and they have been done of course, many times before. And then there's an opportunity to detect ambipolar diffusion directly through the process of molecular ion polarization through collisions. Thank you very much.
Thank you, Boy, for the very nicely presented talk. Well, I have to say this also because not being from this field, I was really able to follow. So thank you for presenting it like that. Any questions for our speaker? Okay. Yes, Ilseng, you can please unmute yourself and go ahead.
Thank you, Boy, for the very nice talk. I'm not expert in this field, but my question might be a bit naive, but I was wondering, you mentioned that the collisional excitation shouldn't be the dominant excitation mechanism to make this approach works. But the observation that you showed, the choice of your lines relatively have the high critical densities. And I'm just wondering, will this approach is working if you see the relatively low density region? If you look at the high density region and apply this, the approach, will that collisional excitation mechanism dominating and your polarization observation will not robustly telling you the magnetic field? Yeah, I'm a bit confused. Could you explain a bit more?
Mm-hmm. Yeah, so I suppose that's why I say I think you're particularly referring to this slide, where I show these simulations for a protoplanetary disk. And indeed, as you say, if we look at CO, then the critical density for this species is very low. So it's really collisions that excite the molecular states. And the expected polarized intensity for a molecule such as CO is indeed very low. So my point that I want to really hammer home is that you really want to be considering a molecule with a very large dipole moment, such as HCN. HCN will have more influence of radiative interactions, and that's why its radiation will polarize more potently than does CO. So you're absolutely right in your observation. Now, the mechanism that I told you about on this slide about collisional polarization, that is something else. Here you really want to have dominant collisions, but this only happens if you have two things: a molecular ion, and you have ambipolar diffusion. So a velocity drift between the ions and the neutral medium, which hosts its main collision partner, H2. Then through oriented collisions, you will polarize or you will align these molecular ions along the drift, along the ambipolar drift, and this will then lead to polarization. So I hope I have answered your question.
Yeah, thank you. Okay, so specifically for the later part, we are actually talking about in the regime of the C shock, correct? It's a high, the supersonic, drift velocity, which is so strong.
Yeah, so a C shock would be very interesting to look at. I've mostly thought only about star-forming regions, so where ambipolar diffusion is really important for the magnetic field transport. So I haven't really thought about molecular ions in C shocks, and because of course, yeah, as you say, you have a very large ambipolar drift in these species. But and this would be a question of me to you. These C shocks, do they span a large enough region to really resolve the shock front where you would expect the highest ambipolar drift velocities? I don't know that, but maybe we can talk about it some more later.
I see. Thank you very much.
Thank you for the nice question. We have Laura Sanchez. Please go ahead and unmute yourself.
Okay, thank you. Thank you for the nice talk. This, I think, is also a very naive question. I'm not familiar with this field, but my question is related to the first plot where you showed the polarized intensity as a function of the offset. So I was just wondering why these two molecules have are polarized in different regions of the protoplanetary disk. So why is this this difference?
Yes, so CO is a molecule that only polarizes at very low densities, and farther away from the center in a disk, you will have lower density. So polarization only arises in the very outskirts of the disk, and already at the point where this polarization is found, the HEN emission will have died out. So that is why.
Okay, thank you.
Yeah.
Thank you, Laura. Also, I would like to mention, Boy, YouTube has a lot of appreciation for you.
Well, thank you very much. Life goals. Life goals.
Any other questions for the speaker? Okay, meanwhile, maybe I can ask a question. I was very happy when you said that you also tried to study an AGN, and I'm myself studying AGN with outflows. So I was wondering if you're also able to estimate the magnetic field directions inside these outflows, or also like at the hotspots close to the core, or is it like a bit?
Yeah. So it's a very interesting problem. I've mostly focused on these CON structures, and this is very biased focus because at our department also Suzanne Alto works, who looks at these embedded nuclei very much so. And particularly if you look at extragalactic polarization, you really need very high sensitivity or very high polarization fractions. And as far as I've been able to tell, this can only be reached through these very specific excitation mechanisms. For instance, through the HEN VIB emission, where the excitation of the HEN is really radiative. And as you will remember from my little explanation, you really need radiative excitation to get these lines to polarize. So I think the HEN VIB is really a perfect storm of polarization in these CON objects. Of course, not all AGNs or not all galactic nuclei will have will be so deeply embedded and will not have this type of emission. But I would be interested to look at other examples. But I think it will be very hard with other molecules. Yes.
Right. Thank you so much. And if there are no more questions, then I would like to thank Boy for the nice talk, and to all those who asked the questions and the audience. Over to you, Giacomo.
Yes, so we are at the end of it was super quick. I mean, at least it flied for me. So thanks to the speakers, because it's thanks to them, because Boy and Virginia, really congratulations, very nice talks and very exciting science. And we are very happy to have you here. So good luck for the rest of the year. But congratulations again. And nothing. So we will continue next week with the program. In the meantime, also just to tell you, Virginia and Boy, now I can tell you there were more than 100 people watching you, more or less, just to keep you. I didn't tell you before. So in total between YouTube, so very.
Thanks for telling us at the end.
Exactly. Exactly. So, but anyway, so thank you also for everyone who attended the talks. The talks will stay online, so we will create also some point a dedicated playlist so you can watch all the events. And with this, we can close. Thank Aish for your nice sharing, mastering the sharing so well. Thank you very much for your help. And Laura and everyone who made questions. So thank you for participating, and see you next time. Bye-bye.
Thank you. Bye.
Oh, bye-bye.